Avery, the applications astronaut, talking to you about a summary of curve sketching. Now I got another question. What's an astronaut's favorite drink in zero gravity? That's going to be a root beer float.
First thing we're going to do is review how to determine the intervals on which a function is increasing or decreasing. So to determine where a function f is increasing or decreasing, the first thing you're going to do is find your critical numbers. And to do that, you're going to set the derivative equal to 0 and then determine any x values that cause the derivative to not exist. The numbers that cause the derivative to equal 0 or not exist, those are your critical numbers. We are then going to take those critical numbers and make a sign chart with intervals that are based on those critical numbers. So typically we are going from negative infinity to positive infinity, and we need to break up that interval from negative infinity to positive infinity based on your critical numbers, and we'll do that in a second. We are then going to pick test x values on those given intervals to plug into the first derivative. So if your interval is from negative infinity to 0, you're going to plug in something like -1 or -2 or -3, a x value that's on that given interval, and you're going to plug it into the first derivative. If that test x value produces a positive number, then your function is increasing on that interval because your first derivative is positive, meaning the slopes of the tangent line to the curve are positive, meaning your function would be increasing. If your test x value produces a negative number, then your function is decreasing on that interval because the derivative is negative. The slopes of the tangent line to the curve are negative. Therefore, your function must be decreasing on that given interval. Now, to determine the intervals on which a function is concave upward or concave downward, it's very similar to what we did with increasing and decreasing functions, except this time we're using the second derivative. So to determine where a function f is concave up or concave down, we're going to find the possible points of inflection first. And to do that, we're going to set the second derivative equal to 0 and figure out any x values that cause the second derivative to be undefined or not exist. Those are going to be your possible points of inflection. We're then going to make a new sign chart with intervals that are based on these possible points of inflection we found in step 1. When we do that, we can then choose test x values on the given intervals that we created in step 2 and plug those in to the second derivative. We are then going to look and see if the test x value produces a positive number, then your second derivative is positive, meaning the f prime of your given function is increasing on that given interval, meaning that your function is concave up on that interval. If your test x value produces a negative number, then your function is concave down on that interval, meaning your second derivative is negative on that given interval, meaning f prime is decreasing, meaning that your function is concave down on that given interval.
What's an astronaut's favorite candy bar? That's going to be a Milky Way. It's example time.
Now example 1 says find the intervals on which the function f is increasing, decreasing, concave up, concave down, and the location of any relative extrema and inflection points. So this is basically combining the last couple sections of notes into one question. So here, it doesn't give us f. It gives us f prime. Well, that's kind of nice actually, because the first step in determining the intervals on which a function is increasing or decreasing is finding your critical numbers of your function. Now the critical numbers, again, occur wherever the first derivative either does not exist or equals 0. So are there any x values that would cause this first derivative to not exist? No, there's not even a denominator. So there's no x values that would cause this first derivative to not exist. So all we have to do then is determine what x values would cause this first derivative to equal 0. So how do we solve this for x then? Well, I need to factor this. Do you remember how to factor a quadratic trinomial? This is actually going to factor into x minus 5 times x plus 1. We then use the zero product property because this times this equals 0. That means either this is equal to 0 or this is equal to 0 over here. We then solve each of these for x. We add 5 to both sides. Here we subtract 1 from both sides, and we have our critical numbers. Next, we want to figure out the intervals on which this function f is increasing or decreasing, as well as any relative extrema. And that all occurs with the first derivative. So we're going to create a sign chart. Now, normally we just break up the sign chart based on the intervals. The only difference we're going to do here is we are going to put the critical numbers in our sign chart. So how this looks is that this function, there are no domain restrictions. So it's going from negative infinity to positive infinity. So it's going to break up based on our critical numbers. So we're going to go from negative infinity to -1. Then at x is equal to -1, we're going to determine whether there's a relative max or min. Then we're going to go from -1 to +5, our other critical number. Then at x is equal to 5, we're going to determine whether there's a relative max or min. And then we go from 5 to infinity to finish out our intervals. Now again, all we have to do to figure out whether the function is increasing or decreasing is pick a test x value on each of these intervals, plug them into the first derivative, see if we get a positive or negative number. So let's pick a test x value on this given interval. How about -2? I'm going to take -2, plug it into the first derivative. I simplify and I end up getting +7. Again, we don't care about the 7, we care that it's positive. Now because it's positive, that means that the derivative of this function on this given interval is positive, meaning that the slopes of the lines tangent to the curve of this function on this given interval are positive, meaning that the function must be increasing on that given interval. Now, what happens at x is equal to -1? We don't know yet. We need to figure out what happens over here. Then we can use the first derivative test. If the function goes from increasing to decreasing, then we're going to have a relative max at x is equal to -1. But if it goes from increasing to increasing, then it's neither going to be a relative max nor a relative min. So let's figure it out. Here, we need to plug a test x value on this interval into the first derivative. How about 0? If I plug in 0 to the first derivative and simplify, I end up getting -5. Again, we don't care about the 5, we care that it's negative. Because it's negative, that means the derivative of this function on this given interval is negative, meaning that the slopes of the lines tangent to this function on this given interval are negative, meaning that the function must be decreasing on this given interval. And now we see that our function f goes from increasing to decreasing at x is equal to -1, meaning at this critical number, there is going to be a relative maximum by the first derivative test. Now, let's check at x is equal to 5 what happens. Again, we need to figure out what happens over here. That way we can use the first derivative test to tell whether x equals 5 is a relative max, relative min, or neither. So we're going to pick an x value on this given interval to plug into our first derivative. How about 6? If I plug in 6 to our first derivative over here for x and simplify, I end up getting +7. Again, we don't care about the 7, we care that it's positive. Because it's positive, that means the derivative of this function on this given interval is positive, meaning that the slopes of the lines tangent to this function on this given interval are positive, meaning the function must be increasing on that given interval. And because your function goes from decreasing to increasing at x is equal to 5, this function must have a relative minimum at x is equal to 5 by the first derivative test. Now let's talk about concavity and the location of inflection points. To do that, we need to figure out what the second derivative of our function is. Figure out the possible points of inflection by setting our second derivative equal to 0 and figuring out any x values that cause our second derivative to not exist. So how do we get our second derivative? Well, we take the derivative of our derivative. So let's take the derivative of our first derivative. Here we take the derivative of each term separately. This is going to be 2x to the first. Derivative over here, the -4 stays out front. You just take the derivative of x, which is going to be 1. So 1 times -4 is just -4. And then derivative of -5 is going to be 0. So we end up getting our second derivative is just 2x minus 4. Now that we have that, we determine, are there any x values that would cause this to not exist? No. So all we have to worry about is what x values cause our second derivative to equal 0. So we set it equal to 0. We solve for x by adding 4 to both sides, dividing both sides by 2. We get x is equal to 2. That means there's a possible point of inflection at x is equal to 2. So we are going to make another sign chart for our second derivative this time. And it's going to look like this. Again, there are no domain restrictions. So we're going from -infinity to +infinity. And the only possible inflection point is at x is equal to 2. So we're going to go from -infinity to 2. And then at x is equal to 2, we're going to determine if there's an inflection point. And then here we go from 2 to infinity. Now, again, to determine concavity, all we have to do is pick a test x value on each of these intervals, plug them into the second derivative here, and then determine if you get a positive or negative number out. So let's pick a test x value on this given interval. How about 0? If I plug in 0 to the second derivative for x and I simplify, I end up getting -4. Again, we don't care about the number, we care that it's negative. Because it's negative, that means that the second derivative of this function on this given interval is negative, meaning that f prime of this function on this given interval is decreasing, meaning that this function on this given interval is concave downward. Now again, we don't know what's happening here yet. We have to determine what's going on over here. If we go from concave downward to concave upward, that means there's an inflection point at x is equal to 2. But if we go from concave downward to concave downward, there would be no inflection point at x is equal to 2. So we pick a test x value on this given interval. How about 3? We plug that into our second derivative and we simplify. We end up getting +2, meaning, again, we don't care about the 2, we care that it's positive. Because it's positive, that means that the second derivative of this function on this given interval is positive, meaning that f prime of this function on this given interval is increasing, meaning that this function on this given interval must be concave upward. And you can see, because our function goes from concave downward to concave upward at x is equal to 2, there must be an inflection point at x is equal to 2. And you're done.
I gotta help Tom Hanks get back from the moon. You try.
Okay, doing the same thing here. So we have a function f, and we're given the first derivative of that already. So we're going to start answering this question by figuring out the intervals on which f is increasing or decreasing. To do that, we need to figure out the x values that cause our first derivative to either equal 0 or not exist. So we're going to set our first derivative equal to 0 and solve for x and find some critical numbers. So how do we solve this for x? Well, we add 81 over x to both sides. We multiply both sides of this equation by x, and then we take the fourth root of both sides, and we get x is equal to positive or negative plus or minus 3. Therefore, we're going to have two critical numbers, x is equal to 3 and x is equal to negative 3. But wait, are there any x values that would cause your first derivative to not exist? Yeah, x is equal to 0. At x is equal to 0, you're going to have a denominator equal to 0, meaning that the first derivative would not exist. So we know that the original function is going to have a vertical asymptote at x is equal to 0. Now, because we have our critical numbers, x is equal to negative 3, 0, and 3, we can now create our sign chart. Remember, there are no domain restrictions here besides x cannot equal 0. So we're going to go from negative infinity to positive infinity. We start at negative infinity and we go to our first critical number, which is going to be negative 3. We then want to figure out at x is equal to negative 3, is there going to be a relative max or min? Then we go from negative 3 to our next critical number. That would be our vertical asymptote at 0. Then at x is equal to 0, we know there's going to be a vertical asymptote. We have to include that in our sign chart because on either side of that asymptote, your function could go from increasing to decreasing or decreasing to increasing. It could change. Then we go from our vertical asymptote at x is equal to 0 to our next critical number, which would be 3. Then at x is equal to 3, we need to determine, is that going to be a relative maximum or minimum? And then from 3, we go to the end of our interval, which in this case is going to be positive infinity. Now again, to determine where our function is increasing or decreasing, we're going to pick test x values on each of these intervals and plug them into our first derivative and determine whether we get a positive or negative number out. That'll show us where the function is increasing or decreasing. So let's start with our first interval here. We're going to pick a test x value on this given interval. How about something that goes in evenly to 81? How about negative 9? I'm going to pick negative 9. I plug that into our first derivative here. I simplify and I end up getting negative 720. You didn't have to pick negative 9. You could pick any number on this interval. I just wanted it to go evenly into 81. Again, we don't care that it's 720. We care that it's negative. Because it's negative, that means the derivative of this function on this given interval is negative, meaning that the slopes of the tangent lines to the curve of this function on this given interval are negative, meaning that the function f must be decreasing on this given interval. Now, at x is equal to 3, we have to determine if it's a relative max or min. But to do that, we need to figure out what's happening here. And then we can use the first derivative test. If it goes from decreasing to increasing, it's going to have a relative min. But if it goes from decreasing to decreasing, it has neither a relative max nor a relative min. So we pick a test x value on this given interval. How about negative 1? I plug that into the first derivative over here and I simplify. I end up getting positive 80. Again, we don't care about the 80. We care that it's positive. Because it's positive, that means the derivative of this function on this given interval is positive, meaning that the slopes of the lines tangent to the curve of this function on this given interval are positive, meaning that this function must be increasing on that given interval. Now, because the function goes from decreasing to increasing, the first derivative test tells us that there must be a relative minimum at x is equal to negative 3. Now, x equals 0. Is there going to be a relative max or min here? Neither. Remember, there's going to be an asymptote at x equals 0, so we can just put that in now. Now, let's determine if the function's increasing or decreasing on this interval. We pick a test x value. How about 1? We're going to plug in 1 for x in the first derivative and simplify. We end up getting negative 80. Again, we don't care about the 80. We care that it's negative. Because it's negative, that means the derivative of this function on this given interval is negative, meaning the slopes of the lines tangent to this function on this given interval are negative, meaning that this function on this given interval is decreasing. At x is equal to 3, we need to determine if there's a relative max or min there. So to do that, we have to figure out what's happening here. Then we can use the first derivative test. So we pick a test x value on this given interval. How about 9? I'm going to take 9, plug that into the first derivative for x, and I simplify. I end up getting positive 720. Again, we don't care about the 720. We care that it's positive. Because it's positive, that means the derivative of this function on this given interval is positive, meaning that the slopes of the lines tangent to this function on this given interval are positive, meaning that this function on this given interval is increasing. Because your function goes from decreasing to increasing at x is equal to 3, we know that there must be a relative minimum at x is equal to 3 by the first derivative test. Now let's figure out where this function is concave down or up. To do that, we need to figure out possible points of inflection. And to figure out those, we need to determine where the second derivative either equals 0 or does not exist. So we need to figure out the second derivative of this function. To do that, we just take the derivative of our derivative. Here, we're going to take the derivative of each term separately. Derivative of x cubed is just going to be 3x squared. Derivative over here, we need to rewrite this as negative 81x to the negative first. Then we could take the derivative, the negative 81 just stays out front, and we take the derivative of x to the negative first. Negative 1 comes out front, multiplies to the negative 81, that becomes positive 81, and this becomes x to the negative second power now. We can then rewrite this as 3x squared plus 81 over x squared. Now that we have our second derivative, we can determine our possible points of inflection. So to do that, we need to figure out where does the second derivative equal 0. So we set the second derivative equal to 0, and we solve for x. So how do I solve this for x? Well, I guess I could subtract 81 over x squared from both sides, multiply both sides by x squared, divide both sides by 3, take the fourth root of both sides. Oh, I can't take an even root of a negative number. So there are no possible points of inflection. But wait, we also have to check, are there any x values that cause the second derivative to not exist? Yeah, x is equal to 0. Remember, at x equals 0, we have a vertical asymptote of our original function. So when we make our second derivative sign chart and our intervals, we're going to go from negative infinity to 0, and then at x equals 0, there's going to be an asymptote, and then from 0 to infinity. Again, why do we break it up at x equals 0? Because the function could change its concavity on either side of the asymptote, so we have to check. Again, we're going to pick test x values on each of these intervals, plug them into the second derivative, and see if they come out positive or negative. So on this interval, we're going to take negative 1, plug it into the second derivative, simplify, and we end up getting positive 84. Again, we don't care about the 84, we care that it's positive. Because it's positive, that means the second derivative of this function on this given interval is positive, meaning f prime of this function on this given interval is increasing, meaning that this function on this given interval is concave upward. Then at x equals 0, we know there's going to be a vertical asymptote. On the other side of that, we're going to pick a test x value on this interval. How about 1? Take 1, plug it into the second derivative, and I simplify. I end up getting positive 84. Again, we don't care about the 84, we care that it's positive. Because it's positive, that means the second derivative of this function on this given interval is positive, meaning f prime of this function on this given interval is increasing, meaning that this function on this given interval is concave upward. So we have determined everywhere where the functions are increasing or decreasing, concave upward or downward, relative extrema, and inflection points. So we are done. Now, example 2 says find the intervals on which the function f is increasing, decreasing, concave up, concave down, and the location of any relative extrema, inflection points, asymptotes, and intercepts. Use a graphing utility to verify your results. So basically, we're combining everything we've learned so far into one example. Now, let's start by finding the intervals on which the function f is increasing or decreasing. To do that, we need to determine where are the critical numbers of this particular function. Now remember, critical numbers occur wherever the first derivative is either equal to 0 or does not exist. So to determine this, we need to figure out what is the first derivative of this function. So we take the derivative of this particular function. Notice that I've taken this 2 and written it out front like this. That way you see that this 2 is actually just a constant being multiplied to x squared minus 9 over x squared minus 4. This 2 then, I can take out front of the derivative sign and multiply it on at the end by the constant multiple rule. That means all I have to take the derivative of is this x squared minus 9 over x squared minus 4. It's going to make it a little bit easier. So anytime you are taking the derivative of a function over a function, the derivative of a quotient, you need to use the quotient rule. The quotient rule says I take the derivative of my numerator, multiply it to the denominator, then subtract the numerator times the derivative of the denominator all over the denominator squared. So now let's go through and simplify this. The derivative of x squared minus 9 is going to be 2x to the first minus 0. Over here, the derivative of x squared minus 4 is going to be 2x to the first minus 0. I then can distribute this 2x to the x squared and to the negative 4. I then distribute this 2x over here to the x squared and the negative 9. I then also have to distribute this negative to the x squared and the negative 9. So it ends up looking something like this. 2x squared minus 8x minus 2x squared plus 18. Now the 2x squared and the negative 2x squared are going to cancel each other out. Negative 8x plus 18x is going to turn into 10x. I then multiply this 2 on and it becomes 20x over x squared minus 4, the quantity squared. Perfect, I have found my first derivative. Now again, why did I do this? Because I need to find the critical numbers. Critical numbers occur wherever the first derivative is either equal to 0 or does not exist. So let's determine where this equals 0. To figure out where this is equal to 0, all we have to do is set the numerator equal to 0 and solve for x. So here we divide both sides by 20, we get x is equal to 0. That is one of our critical numbers. That causes our derivative to equal 0. Are there any x values that would cause our derivative to not exist? That would be x values that cause our denominator to equal 0. So what x values cause our denominator to equal 0? Well, it looks like it would be 2 and negative 2. So all of our critical numbers then would be negative 2, 0, and 2. Now I'm going to create a sign chart to determine where our function is increasing or decreasing. And it's going to be based on these critical numbers. So the only domain restrictions that we have here in our original function would be that x cannot equal 2 or negative 2 because that would cause our denominator to equal 0, meaning there's going to be an asymptote at x is equal to negative 2 and an asymptote at x is equal to positive 2. So we're going to break up our intervals based on our critical numbers, and negative 2 and positive 2 are in our critical numbers. So that accounts for these asymptotes up here. So we start from negative infinity and we go to our first critical number at negative 2. Then at x is equal to negative 2, we have to determine what is happening in the graph. Then from negative 2, we go to our next critical number, which is at 0. Then at x is equal to 0, we have to determine what's happening in our graph. Then from 0, we go to our next critical number, which is 2. And then at x is equal to 2, we have to determine what's happening in our graph. And then lastly, we go from 2 to infinity. Now, let's determine where this function is increasing or decreasing. To do that, we're going to pick test x values on each of these intervals to plug in to our first derivative and determine what sign we get out. If we get out a positive number, it means the function is increasing. If we get out a negative number, it means the function is decreasing. So let's first start by picking a test x value on this interval. How about negative 3? If I plug in negative 3 to my first derivative and simplify, I end up getting negative 60 over 5 squared, which becomes a negative number. Because it's negative, that means that the derivative of this function on this given interval is negative, meaning that the slopes of the lines tangent to this function on this given interval are negative, meaning that this function on this given interval is decreasing. Now, at x is equal to negative 2, what's happening? Well, we said in our original function, x squared minus 4 factors into x plus 2 times x minus 2 in our denominator, meaning that there's going to be a vertical asymptote at x is equal to negative 2 and x is equal to positive 2. So at x is equal to negative 2, there's going to be a vertical asymptote. After that, we have to choose a test x value on this interval. How about negative 1? If I plug in negative 1 to my derivative and I simplify, I end up getting negative 20 over negative 3 squared. Negative 3 squared is going to become positive, so we have a negative number over a positive number. That's going to be negative, meaning that the derivative of this function on this given interval is negative, meaning that the slopes of the lines tangent to this function on this given interval are negative, meaning that this function on this interval is decreasing. Now, at x is equal to 0, is there an asymptote? No. So here, we know that this is a critical number, meaning that there must be a relative max or min here. So to determine that, we need to figure out what's going on in this interval. If it goes from decreasing to increasing, there's going to be a relative min at x equals 0. If it goes from decreasing to decreasing, though, there's neither a relative max nor a relative min. So we pick a test x value on this given interval, plug it into our derivative. How about 1? If I plug 1 in, I simplify, I end up getting 20 over negative 3 squared. Now, negative 3 squared is positive, so we have a positive number over a positive number, meaning that we get a positive number. Now, because this is positive, that means the derivative of this function on this given interval is positive, meaning that the slopes of the lines tangent to this function on this given interval are positive, meaning that this function on this given interval must be increasing. Now, by the first derivative test, because your function goes from decreasing to increasing at x is equal to 0, we know there must be a relative min at x is equal to 0. What about x equals 2? Well, to determine what happens at x equals 2, we remember in the beginning, our denominator factored is x plus 2 times x minus 2, meaning that there is a vertical asymptote at x is equal to negative 2 and x is equal to positive 2. Because there's a vertical asymptote, there can't be a relative max or min there. Now, from negative 2 to infinity, we need to figure out, is it increasing or decreasing? So we pick a test x value on this interval. How about 3? Plug it into our first derivative. We then simplify, and we end up getting 60 over 5 squared. Positive number over a positive number, that means this is positive, meaning that the derivative of this function on this given interval is positive, meaning the slopes of the lines tangent to this function on this given interval are positive, meaning this function on this given interval must be increasing. Now let's check out concavity. So to figure out whether the graph is concave up or concave down, we need to determine the possible points of inflection. To figure out the possible points of inflection, we need to determine where the second derivative either equals 0 or does not exist. So to do that, we need to figure out what is the second derivative. So we take the derivative of our first derivative. To do that, again, we have a function over a function. So to take the derivative of a quotient, you need to use the quotient rule. So we take the derivative of our numerator, multiply it to the denominator, minus the numerator times the derivative of the denominator denominator all over the denominator squared. Now we take the derivative here. Derivative of 20x, the 20 just hops out front. Derivative of x is just 1. Over here, the derivative of x squared minus 4, the quantity squared, requires the chain rule. So this becomes 2x squared minus 4 to the first power times the derivative of x squared minus 4, which is just 2x to the first minus 0. Now, you see that each term here has an x squared minus 4. We have an x squared minus 4 over here and an x squared minus 4 over here. So I'm going to factor out x squared minus 4. I do that because now in here, this simplifies a little bit easier. 20x times 2 times 2x becomes 80x squared. And then over here, 20 I distribute to the x squared and the negative 4, and that becomes 20x squared minus 80. Now, the reason we factored out this x squared minus 4 is because there's an x squared minus 4 to the fourth power in our denominator. So this will cancel out with one of these, leaving this as x squared minus 4 to the third power in our denominator. We can then simplify our numerator. 20x squared minus 80x squared becomes negative 60x squared. We can then factor out a negative 20, and we end up getting something that looks like this. So we have our second derivative. Now remember, we did this because we're trying to find the possible points of inflection. And inflection points occur wherever the second derivative either equals 0 or does not exist. So first, are there any x values that would cause this second derivative to equal 0? Well, we just need an x value that would cause the numerator to equal 0. So let's take the numerator, set it equal to 0, and solve for x. So we divide both sides by negative 20, we subtract 4 on both sides, divide both sides by 3, and then we have to square root both sides. Oh, we have to square root a negative number? Well, that's not going to give you a real number, therefore there are no real x values that would cause your second derivative to equal 0. Well, are there any x values that would cause your second derivative to not exist? Well, those would be x values that cause your denominator to equal 0. And we said those would be 2 and negative 2. But we can't include those as possible points of inflection because, as we already saw, at x is equal to negative 2 and positive 2, we have vertical asymptotes. So, because there's no real x values that would cause your second derivative to equal 0, and at the x values that would cause your second derivative to not exist, there's asymptotes, we know that there are no possible points of inflection. Now, even though there are no possible points of inflection, we still need to figure out where the graph is concave up or concave down. So we're going to create our sign chart. We're going to still break up our sign chart, though, based on the vertical asymptotes, because this function could change from concave down to concave up, or concave up to concave down on either side of the vertical asymptotes. We need to check. So our intervals are going to start from negative infinity and go to our first vertical asymptote at x is equal to negative 2. Then at x equals negative 2, we're going to have that vertical asymptote. After that, we're going to go from negative 2 to positive 2, which again, we have our vertical asymptote at. And then lastly, we're going to go from 2 to infinity. Now we pick test x values on these given intervals to plug into our second derivative this time and determine whether the graph is concave upward or downward based on the sign of the number we get out. So let's choose on this first interval. How about negative 3? I'm going to take negative 3, plug it in the second derivative for x, simplify, and I end up getting negative 20 times 31 over 5 cubed. This is going to end up being negative, which means the second derivative of this function on this given interval is negative, meaning f prime of this function on this given interval is decreasing, meaning that this function on this given interval is concave downward. Again, at x equals negative 2, we have that vertical asymptote. Now we check on this side of the asymptote. We pick an x value on this interval. How about 0? I'm going to take 0, plug it in for x in our second derivative over here. I simplify. I end up getting negative 20 times 4 over negative 4 cubed. Now negative 4 cubed, that's going to be negative. This up here is also going to be negative, which means we have a negative over a negative. That makes it positive, meaning the second derivative of this function on this given interval is positive, meaning that f prime of this function on this given interval is increasing, meaning that this function on this given interval is concave upward. At x equals 2, we have our second vertical asymptote, and then we pick a test x value on this interval now. How about 3? I take 3, plug it in for x in this second derivative, and I simplify. I end up getting negative 20 times 31 over 5 cubed again, which we said was negative. That means that the second derivative of this function on this given interval is negative, meaning f prime of this function on this given interval is decreasing, meaning that this function on this given interval is concave downward. Now that we figured out the increasing and decreasing intervals, the concave up and down intervals, the relative extrema, and the inflection points, we need to determine the asymptotes and the intercepts. So asymptotes, we already said that this function has vertical asymptotes at x is equal to negative 2 and x is equal to positive 2. Horizontal asymptotes, though, we know that this function actually will have a horizontal asymptote because we have a rational function which has the same degree in the numerator that it does in the denominator, which means that it's going to have a horizontal asymptote at y equals whatever the ratio of the leading coefficients is. Well, that would be 2 over 1. So this is going to have a horizontal asymptote at y equals 2. We then determine the x-intercepts by plugging in 0 for y and solving for x. So we're going to plug in 0 for f of x in this case. Now again, the only way this would equal 0 is if the numerator equals 0. So we're just going to set the numerator equal to 0 and solve for x. Here I can divide both sides by 2. I just get x squared minus 9 is equal to 0. I can then factor this into x minus 3 times x plus 3. And since this times this equals 0, I can use the zero product property and set this equal to 0 or this equal to 0. I can then add 3 to both sides. I get x is equal to 3. I can then subtract 3 from both sides. I get x is equal to negative 3. So I know that my two x-intercepts are going to be at 3, 0 and negative 3, 0. For my y-intercepts, I'm going to plug in 0 for x and solve for y. So when I plug in 0 for x and I simplify, I end up getting 2 times negative 9 over negative 4, which simplifies to negative 18 over negative 4, which simplifies to positive 9 over 2. So I know that my y-intercept then of this function is going to be at 0, 9 over 2. Now let's confirm all of this with a graphing calculator. So first, we see that our interval from negative infinity to negative 2, our graph is both decreasing and concave down. That checks out. We also see that one of our x-intercepts is here at negative 3, 0. That checks out. Then we know there is one of two vertical asymptotes at x is equal to negative 2. From negative 2 to 0, we know that the graph must be decreasing and concave up, which it is. Then, at this particular point, we have a y-intercept that would be at 0, 4.5 or 0, 9 over 2. Also at this particular point, we know there must be a relative minimum value, which there is. From 0 to 2, we see that the graph is both concave up and increasing now. At x equals 2, we have the second of our vertical asymptotes. After that vertical asymptote, the graph must be increasing and concave down, which it is. And we have our last x-intercept at 3, 0.